you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready? Are you ready to go?
Hello, it's Mr. T here, and today I have a tutorial on something called series. In our last tutorial in this unit, we talked about sequences. Sequences were sets or lists of numbers that had some sort of pattern. And today we're going to extend that where the series is the sum of all those terms. So we'll be adding all the terms of the sequence together. This is an example on the picture here of something called Sierpinski's triangle. And if we were looking at, after some number of stages, how much of the blue area remains, we could use that and create a series for that and calculate that sum. So here's a couple examples. Here's a sequence similar to what we did before. We can see here that as we increase, each number is going up plus 3. So that is an arithmetic sequence. And if we turn that into a series, we would be just adding each of those terms. And this time we just add those up and we get 45. Later in the video, we'll be talking about some formulas that will help us calculate sums of these series, especially if we had, say, 50 or 100 terms here. We wouldn't want to have to list them out and add them up. Now, this is an example of a finite sequence, therefore it's a finite series. It had a specific number of terms. To the right is an example here of another sequence. It's the same sequence here, so it's another arithmetic sequence. But remember, the significance of dot, dot, dot here is that this sequence goes on forever, so it's an infinite sequence. And in this case, we would add that series together, but since we're adding an infinite number of numbers that are increasing, we are going to get an infinite value for the sum. As we go through this, we will find that some infinite series, not this one, will have a finite sum. That's a little bit kind of mind-boggling that we will be adding together an infinite number of numbers, but we will get a finite answer for that. So we'll see that later. Need to introduce some new notation. This is called sigma notation or summation notation. This is the Greek capital letter sigma, and we use it as a shortcut notation for depicting series. So we have a rule here, and we can use any letter here, I, K, N, whatever. And at the bottom we have the starting number that we're going to use for I, and at the top is the ending number. So if I was going to expand out this series here, we would start with and do I equals 1, 2, 3, 4, and 5. And we would plug those i's in this formula. So here we've got 3 times 1. And here we would have 3 times 2, 3 times 3, 3 times 4, and 3 times 5, and the sigma means summation, so we would be adding all of those numbers together. So this would be which is the same problem that we just had on the previous page. So this is the summation notation or sigma notation for this series right here, a finite series. And we had calculated that that value was 45. So this has a value of 45. This one has the same 3i, so this would be the representation in sigma notation for this infinite series. So we could start writing these out. Again, this would be start at 1, so 3 times 1 plus 3 times 2 plus 3 times 3. But we don't stop here because we keep going to infinity. And we showed on the last slide that this would be, value would be infinity. So this one, infinity. Now, just as another example to get used to this notation, this one's a little bit more complicated, but we'll expand this out. So remember, we're going to start with I equals 1 and plug it in. So we have 1 over 1 plus 1. And now we go I is 2. And we're just plugging in for both i's. We could simplify each of these fractions. So this is 1/2, and this is 2/3, and this is 3/4, and this is 4/5, and 5/6, and we could add those up. I'm not going to take the time to add these up. You could use a calculator, or you could use good old math and get common denominators for all this. But the main thing was how to interpret or use this sigma notation. Now, just like, before we get to that, there are some of these special formulas, we might want to call them, or sigmas that have formulas for calculating their sums. If you take a discrete math class, there are lots of these sums that have defined rules. I've listed some common ones here. Now here in this one, k is not the I here, so this is a constant. So if we were adding this up, it would be the same number over and over. Like, so if k was 3, so let's say this was the sum from I equals 1 to, say, 6 of 3. Now, so 3's are k. This would be 6 3's. Now, we're not putting the i's in because there's no I, but we still have to do the number of terms from 1 to 6. I need one more. And we know that that would be 18. But we've got here 6 3's. So it's n times k. So that's this formula here. Let's look at an example of what this is doing. If we do the sum, say, from I equals 1 to 10 of I, now that's going to be 1 plus 2 plus 3 plus 4 plus 5 all the way out to plus 10 if that was 10. So that we can use that to find the sum of integers. So we're going to use that when we get down to these problems down here. So again, instead of listing out a bunch of numbers, say this was 100 or 1,000, we can use this formula to calculate that total sum. And here we have I squared, so that would be the sum of the squared. So if we were doing I'll just keep it short this time, to 4 of I squared, it's going to be 1 squared plus 2 squared plus 3 squared plus 4 squared, which would be 1 plus 4 plus 9 plus 16. And we could, in this case, with just 4 terms, add those up rather quickly. But if we wanted to do, say, this sum for n being some big number, we can use this formula. So we're going to be using this formula because we're talking about sum of integers here. So we could represent this first problem here as the sum I. Let me fix that. I don't want to use n because we've got that at the top here. So I equals 1 to 50 of I. So that would be 1 plus 2 plus 3 plus 4 up to 50. But if we want that sum, we can use this formula here. So n is 50, so it's going to be 50 times 50 plus 1, which is 51, all divided by 2. So this would be, if we multiply those together, we get 2560, I think, here. So we would have 50 and 2500. No, I'm sorry, that would be 50 plus, yeah, that's not right. I did that wrong. So that would be 2550. The top here is 2550 divided by 2. So if we divide that, we get 1, 2, This would be 15, so that's 7 and a 10, so 1275 if I did my math right. Let's just double check. My brain is not working well here, so let's just check that. So 50 times 51 here, and divide that by 2. And yes, I did that right, 1275. So now let's look at our second problem. A little bit more complicated. Here we want to find the integers, the sum between 50 and 100. So one way of doing that using this notation, because this rule starts at 1, we could find the sum of the first 100 numbers. So that's 1 through 100. And then we would have to subtract to that the numbers up to 49. So we would subtract from that the first 49. And that sum would give us our answer we're looking for. So here we've got, using our formula up here, we've got 100 times 101 divided by 2. And from that we're going to subtract 49 times 50 over 2. So let's calculate that. So we've got 100 times 101 divided by 2. And from that we need to subtract this quantity here, 49 times 50 divided by 2. I guess I didn't want this. I want that parentheses. I don't want this parentheses here. And we get 3825. Again, that is the sum of the numbers starting at 50 and going up to 100. So if you study some higher level math, you might have to learn and memorize some more of these formulas. I did when I was in college. All right, so just like when we talked about sequences, we have two kinds of series. We have arithmetic series and geometric series. Remember, on arithmetic sequences, they had a common difference. So the adjacent numbers, we kept adding d over and over, and this is our formula for writing the rule to find the nth term of an arithmetic sequence. And now we have a formula here for finding, now this notation, capital S with a little n, a subscript, means finding the first n terms of an arithmetic sequence. And we have a formula here. So these are like special formulas, like similar to what we have with the sigma notation, but these are specifically tuned towards these arithmetic series. So if we want to find, say, the first 30 terms in this arithmetic sequence, now first we can verify that it's arithmetic because we're adding 3. Add 3. Add 3. So our d value is 3. And our first value is 4. So if we want to write a formula for the nth value, using our formula that we had in the last video, it's going to be the first term plus 3 times n minus 1, and this is our d. Now to find this sum, so it's asking us to find sum sub 30, it's going to be 30 times, now we need to find a1, which is 4. And now we need to find the 30th term, a sub 30. So using our formula here, a sub 30 would be 4 plus 3 times 29. So this is 127 plus 4 is 131. And we divide that by 2. And now we can calculate that. So in our parentheses here, we have 135 divided by 2. And now we need to multiply that times 30. And we've got 2025. Meaning, if we had taken and listed this sequence following this pattern and listed 30 of these terms and added them all up, this is the number that we would get. Now, for arithmetic sums, since this number is continually increasing, if we tried to add an infinite number of things, so if we tried to find, say, s sub infinity, that's going to be an infinite number. So we can only find sums for arithmetic series that are finite in length. All right, now we're going to look at geometric, and we're going to look at it in two parts. We're going to first look at finite geometric series, and then we'll look at infinite and see what happens there. Now, as you remember from the last video, geometric sequences have a common ratio, meaning we are repeatedly multiplying by some number. And this is how we can write a rule for the nth term. So given that, and actually we don't need this rule on a geometric. The rule here for the sum of the geometric is much easier. All we need to know is the first term and our common ratio. So this is our formula that you'll be using for geometric series, finite ones. So if we have this geometric series here, remember going from here to here, or not remember, but we can identify that we're multiplying by 5. Here we're multiplying by 5, etc., times 5. So our common ratio is 5, and our a sub 1 was 1. So if we want the first 15 terms here, s sub 15 for the geometric, it's going to be a sub 1, which is 1, and then 1 minus 5 to the nth power, so in this case would be 15th power, divided by 1 minus 5. And we're going to need a calculator to calculate that. So we've got 1, and then I need a parentheses for this whole thing. And I need to put both my top and my bottom. When we have a fraction bar, I need to put parentheses here and here. Otherwise, the calculator is not going to give you the order of operations that you're expecting. So 1 minus 5 raised to the 15th power. And then we're going to divide that by 1 minus 5. Could have just typed in the negative 4 there. And close our parentheses and press enter. And you can see we're getting a really big number here. Let's see, 7, 6, 2, 9, 3, 9, 4. Whoops, move that over. 5, 3, 1. Put some commas in so we can see how big that number is. And we get 7,629,394,531. Usually when we're dealing with geometric series here, even when the r value is bigger than 1, these grow quite rapidly. So we can't be asking about what's the sum of, say, the first 100 or 1,000 numbers. We'll get too big of a number. Now let's look at what if we have a infinite geometric series, and can I add up each of these numbers? Can I add up an infinite of these numbers and get a finite answer? So here, every time we go, our common ratio here is 1/2. So we are multiplying by 1/2. Now if we look at this in terms of geometrical terms with an area, we're starting out with half of a object. So our first thing that we're adding is 1/2. So I'm going to shade in the part that we're adding. So we've added in the 1/2 here. Now we're going to add 1/4. Well, that was 1/2. So half of the half is 1/4. So now we've added in this amount. Now an eighth is a half of the 1/4. So this is a 1/4, and we're going to add half of that. And then we add a 16th. That's going to be half of this eighth. And you should be able to see what's going to happen as we keep filling in. Now if we have a really sharp pencil, we're never going to completely fill it in, but you can see we are getting closer and closer to completely filling that square. So if we view this square as having a area of 1, because we were doing fractions of that unit, when we add all these together, we're going to get the number 1. So again, we are adding an infinite number of numbers, but it adds up to a finite number, in this case 1. Now, not all geometric sequences, as we can see in the previous one, will add up to a finite number. If we kept this going for an infinite number, we're going to see we're going to get and head towards really, really large numbers, so to infinity. So the difference here is our common ratio was a value that was less than 1. So our rule for infinite geometric sequences, or series, are shown here. Now, we could show s sub infinity, but we just use the letter s. So if there's not a subscript here, it's talking about the infinite geometric series. And it's a sub 1 over 1 minus r. And again, provided that the common ratio, or its absolute value, is less than 1. And when we have a finite sum of an infinite series, we can say that that series converges. If our common ratio is bigger than 1, then we're going to add up to infinity, and that's called diverging. So let's look at this example. So going from here to here, we're multiplying by negative 1/4. And going to the next one, we're multiplying again by negative 1/4. So our r value is negative 1/4. If we take its absolute value, it's 1/4, which is less than 1. So this series will converge. And if we want to know what it converges to, we can use our formula up here. So it's going to be a sub 1, which was 1, divided by 1 minus our common ratio, which was negative 1/4. So this is 1 over 5/4, which would end up being 4/5. So if we added all of these fractions, and remember some are positive and some are negative, so they're like canceling each other out, but it would add up to the number 4/5. So let's wrap up this tutorial here with two quick examples. Here we have a honeycomb that bees are making. Now, we're starting counting our series here the way this picture is drawn with the first ring. So the first ring are these cells around here. This is sort of our priming. So we had one cell here, but here we added, there's 6 sides, so we added 6 cells. Let me make that a darker color here. So there are 6 cells in this ring. If we count in ring 2, we've got 1, 2, 3, 4, 5, 6, 7, 9, 10, 11, 12. So we have 12 cells. And we can see if we keep going, or we could draw the picture, what we're adding each time is we are adding 6 cells to each ring. So our rule for the nth ring is going to be 6 times n. Now, if we wanted to know the total number of cells after we get n rings, so not just the outer ring, but the total number of cells, we would be finding the sum of 9. But remember, we didn't count this, so we've got to count that one cell in the middle. If we only did this here, we would be counting all the rings, but we would not be counting that initial cell. So we have to add 1 to that. And using our formula that we had for s sub 9, now this is an arithmetic sequence because we're adding. Remember, it was n, which in this case is 9, times a sub 1, which is 6, plus we need a sub 9. So if we put 9 in here, we get 54, divided by 2. So here we have 1 plus 9. Now this would be 60 divided by 2 is 30. So we get 271. So this honeycomb, after 9 rings, we would have 271 cells. Now let's look at our last one here. We have a basketball that's being dropped. Now we're just going to look at part A here on this one. A basketball is being dropped, and every time it drops based on the resiliency or the elasticity of this basketball, it bounces up to 80% of the previous height. So when we go to the next height, we are multiplying by 0.8. So 10, we get 0.8 times 0.8. Now we're looking for now this would theoretically keep going. It really never stops bouncing using this model. But we might want to know the total distance traveled. Now we have down distances and up distances. So for down, our sequence starts at 10. So that's our A sub 1. And our R value is 0.8. So our sum, our infinite sum here, because we want it to keep going, is A sub 1, which would be 10 over 1 minus R. Now we know this converges because our R value is less than 1. So we get here 10 over 0.2, which is 50. So that this is in feet. So our total down distance is 50 feet. For up, our first up is 8 feet. So on this sum, so this is for up and this is for down, we've got 8 over, and again our common ratio is still 0.8 because it goes up the same distance that it came down. I mean, well, it's going up the 80%, but it's got to come back down before it bounces again. So now we've got 8 over 0.2, which is 40, and we have to add those together, so we get a total of 90 feet. So sorry this tutorial is a little long. Good luck in working on sequence and series, and see you around.
Are you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready? Are you